So welcome. This is VXLAN and VPC best practices in design. I'm going to talk about how two of them interact with each other. My name is Nemanja Kamenica, and I'm technical marketing engineer at Cisco. I've been at Cisco for about 8 years, focusing on the data center product line, which is Nexus switches, but also data center technologies like VXLAN, VPC, QoS, multicast, and different platform stuff. So a couple of housekeeping items for beginning of the session. If you have a question, feel free to raise your hand. I'll pick it up as soon as I can to finish whatever I was speaking. For whatever reason, if you don't remember, forget, or whatever reason you don't get to ask me a question, there is WebEx space. So find it there, ask the question, I'll pick it up today, tomorrow, during the show, or when I get home. Doesn't matter, just ask the question. I'm here to help you. Another housekeeping item, the session is about 45 minutes. So there is a lot of hidden slides which are there to explain certain concept, which I'm gonna touch base, but I might not have time to explain it in all the details. So look for the hidden slides. Once I go through the session, there is a page number over here. You will see how I'm skipping those. So you'll see where the hidden slides are. With that, let's just look what are the objectives for this session. We do have, first, to get you some more knowledge about VPC and VXLAN and how VPC interacts with hosts and as well VXLAN in underlay and overlay. The assumption is that you are familiar to some point with VPC as well as VXLAN. Here we are just connecting to each other and kind of understanding the concept which they have with each other. Introduce you to VPC fabric peering, which is a newer technology and some advanced way to connect VPC to VXLAN environment. And then go to understanding of all the best practices or best practices when you create VPC in the VXLAN. So I'll show you what I mean by that during the session. With this, let's go to a brief introduction, why it's VPC there and what it does. So why VPC? If you would have a simple network of 3 switches, so we have switch 1 and switch 2 on the top, connected to switch 3 on the bottom. What will happen if you run spanning tree over here? One link will be blocked, which means you lose half of the bandwidth which the switch 3 talks to switch 1 and switch 2. Not really a good solution. What you can do is to tell to switch 1 and switch 2, hey, 2 of you are working together. You are creating a VPC domain. And to switch 3, you are represented as a single logical layer 2 switch connected over port channel. So what it means to switch 3, I can use all of the links, I have faster convergence time, and I have more bandwidth, meaning I use all the links. So that's main reason why you would use that VPC and what are the benefits. But where you can see VPC, in data center evolution, you can see it everywhere. So we started building data center networking and data center fabrics with spanning tree. Same problem, you have half of the link are blocked because you need to mitigate the loops with spanning tree. So it wasn't so efficient solution. So what we have done, we built solution with VPC. So you can build your aggregation layer to access layer, connecting it through VPC, but also you can connect your host to a VPC to access layer through a VPC. So you dual home them, getting all the possible bandwidth and all the benefits of the VPC. What we have done next, we introduce fabric path, as well having VPC from the host to the access layer, giving that dual home capabilities and additional bandwidth which you have. This flavor of the VPC is called VPC Plus because it works with fabric path, as I mentioned. And then after that, we evolved to VXLAN flood and learn, similar to any kind of layer 2 network, where we kind of flood that information about the host. But again, you see VPC connecting to the host, dual homing that host to 2 leaves, providing additional redundancy and additional bandwidth. And 2 latest technologies in the data center at Cisco are ACI, application-centric infrastructure, as well as VXLAN with BGP EVPN control plane. My main focus will be VXLAN BGP EVPN in this session, and I will explain how VPC interacts with that fabric. But even here, you can see that hosts are dual home to the access layer of the network, again, leveraging that benefits of the VPC. With this, I'm just going to go straight to VPC and VXLAN and explain how VPC interacts with VXLAN. So what we do here is that we have a set of hosts on the bottom, which are dual homing to the access layer of this fabric. When we talk about the fabric, we have two concepts when it comes to VXLAN called underlay and overlay. Your underlay is a transport network built of switches running some kind of IGP routing protocol, for example, OSPF, transporting that encapsulated traffic in that network. And then in overlay, you have BGP EVPN transporting or advertising host information. And then at the access layer, all of your leaf switches or certain amount of switches are VTAPs, which is virtual tunnel endpoint, which is a termination point for VXLAN encapsulation. So at this point, we encapsulate the traffic into VXLAN header, and on the other side, we de-encapsulate the traffic out of that VXLAN tunnel. So that's why it's called overlay and underlay. But before we go into VXLAN, let's figure out how these hosts interact with VTAPs, or in this case, with VXLAN's leaf switches in this fabric. So what we have here, we have something which is called distributed anycast gateway. What that means is that we have a set of SVIs, which are advertising, which are gateways for any hosts which are part of that VLAN. So we can configure multiple SVIs. Let's say start with VLAN 100 and configure VLAN interface 100, assign the network address to it, which is in this case, or gateway address to it, assign gateway address to it, which is 192.168.10.1/24. We can have multiple SVIs. Each of them will have their own network and their own gateway address for all the hosts which are belonging to that particular VLAN. And what also you need to do is to configure anycast gateway MAC address, which will be the same for all the SVIs present on that fabric. So how do you do that? You first configure the MAC address, which is top line in this little example. And then you configure your interface VLAN 100 and 200. You assign the network address to it. And at the end, you say fabric forwarding mode anycast gateway, saying to this particular SVI, you are behaving as anycast gateway. So what this means, if you would have a host which are attached to this leaf switches, they would send an ARP request from the host to the edge of the fabric, and they would get ARP response with that gateway IP address, which is assigned to that SVI, and that MAC address, which we have defined in the previous example. And they always go to the nearest leaf. So directly attached leaf, those ARP request, if this is a routed traffic, never goes over the fabric. It always terminates at the nearest possible leaf. So how this interacts with VPC works exactly the same as for any other host. You send ARP request to the nearest leaf, and you get that same SVI IP address as your gateway and that same MAC address. You don't need to configure any of the first hop redundancy protocol like HSRP and VRRP. Anycast gateway does provide you that capabilities across all the switches in the fabric, including both of the VPC peers. And also the port channel hashing from the host itself to any of the links basically mitigate duplication of those ARP requests, so you are protected there as well. So this is how the hosts are interacting to the leaf in the host segment, basically access segment. But and how they interact with VPC as well. But let's figure out how VPC interacts with overlay. So in overlay, we do have a VTAP address or NV interface and its address on it. but each box, each VPC peer will have its own individual identity. And two of them, part of the VPC domain, they get unique identity which is common for that VPC domain. So how that looks like from IP address perspective, first, we do have that each VPC peer, or VPC1 on the left, yes, on the left, it has IP address 10.200.200.102. Our VPC peer on the right, VPC2, has IP address 10.200.200.103, but our Anycast VTAP address is 10.200.200.123. So our VPC domain will be represented to the rest of the VTAPs with this VIP address, which is 10.200.123. So let me show you an example where you configure this, and this will be a little bit more clear. So you configure two loopbacks. One loopback is your router ID, used by routing protocol, which you have there, as I mentioned, OSPF, for example, to advertise itself. But also you configure another loopback, loopback 1, which will be your source address for your NVE interface. And in this interface, you configure primary IP address, which is that unique identity of each switch in the fabric. And for the VPC domain, you do configure the secondary IP address, which is that VIP address of the fabric, of the VPC domain itself. I'll show you why we configure this and how this IP address is used. So in short, this is what's going on. However, let's look how hosts are advertised inside of the VPC domain. So in this case, we do have a host A, which let's say has sent an ARP request to our leaf or VTAP on the left in VPC domain. And that leaf has advertised this host using type 2 routes. So when I said you're somewhat familiar with the VXLAN, I'm assuming you do know what are type 2 routes. They're used to advertise hosts. And they can advertise layer 2 and layer 3 information about the hosts. In this case, we advertise, we send type 2 route from that host A. You see type 2 over here, which advertise the type. You send the MAC address of the host itself. And then you send layer 2 VNI, which is kind of your VLAN for any kind of bridging traffic. That layer 2 VNI, it's assigned, you configure it, and it carry as well the route target, which is AS number, BGP AS number, and that VNI number. And then you kind of advertise the layer 3 information about the host, which is IP address of the host, 192.168.10.101, and the layer 3 VNI and the layer 3 route target. Again, layer 3 VNI and route target, it's AS and that route target or VNI identification. And then most important thing when it comes to VPC, the next hop is that VIP address, that secondary address of the NVE interfaces, which both of the switches in the VPC domain have. So that's the next hop address which we advertise for this particular host. Let's say other VPC peer learns about this host and advertise this host. It advertises it with exactly the same route, or at least what it seems to be exactly the same route. However, it is not. These two routes are distinguished with route distinguisher. So the rest of the fabric does know that there are two devices which are representing this host. So I can load balance between these two devices using ECMP, which is equal cost multipath. So that's how this is done, and this is how that host is advertised by VPC to the rest of the fabric. Once when we have this host, let's see how host B, which is on our right side, sends traffic to host A, which is on our left side. So all these blue lines in the diagram are physical links, physical connections present between two VTAPs and the spine, or three VTAPs and the spine, where two VTAPs are in VPC domain. And these green dotted lines, it's our BGP peering, BGP EVPN peering, where those two VTAPs or VPC domain and the other VTAP learn routes from each other. So our host B knows that it has two paths to reach at least two paths to reach to the VPC domain. So when it sends traffic, at any given point in time, can use any of the available paths to reach the host B, and that's what underlay provides to you. Basically, a transport between two of the VTAPs for your traffic to be forwarded. So I did mention this, and let me just kind of repeat. So when we advertise information, type 2 routes, which is our host routes, which I explained in the previous example, we advertise it with VIP address. You can see it in the table on the bottom right that we advertise it with VIP address. And then for our type 5 routes, which are information about IP subnets, we advertise with type 5 routes. I'll come to those in just a moment. But they're also advertised with that VIP address, address which is made out of the VPC domain. So what information about router MAC address or MAC address we advertise, and I'll show you where in the next example. We do advertise MAC address, and we use router MAC address. So brief explanation of the router MAC address. When you set up the switch and you boot it for the first time, if you go and do show MAC address table, you will see that one MAC address exists, and it's tied to the SUP, to the supervisor module of the switch. So that's your router MAC. And any time when any of the endpoints or has a destination of that MAC address, that means to that switch, to that router, that this particular packet needs to be routed. So that's what that router MAC address. So for any routes, type 2 or type 5, either those are connected through VPC or to orphan ports, we do advertise with VIP and our MAC, router MAC, in any of the advertisement. So let me show you this in a little bit better example. So in this case, we do have host B on the bottom, and we advertise it by both VTAPs, our VPC domain, with 2 routes, which are on the top right side. You see that we advertise it with type 2. We advertise layer 2 information, MAC address, layer 2 VNI, and route target. We advertise the IP information, the IP address of the host, and we do advertise layer 3 VNI. And you see that both of those VTAPs the next hop in both of the routes is VIP address of the VPC domain, which is 10.200.200.123. And the only point which differs between these two advertisements, it's external community, which is IP address of the router, which is router MAC. So the rest of the fabric does know that can reach that host B over both of the VPC VTAPs or the VPC domain in this case. So any route can be taken. And when we see how this packet is encapsulated, we see in this middle packet, we see that source IP and destination IP are IP addresses of the VTAP. So our Tor1 has IP address 10.200.200.101, and our destination is VPC domain with 10.200.200.123. Because we do bridging, we do layer 2 VNI, and our MAC addresses are the same. Because we are not routing, we use host MAC addresses to kind of forward this traffic. And then we go and use destination IP, source IP and destination IP of the host. One packet is encapsulated. We basically forward the same packet over here. So before I continue further, any questions so far? Go ahead.
What happens if the link between Tor2 and host B is down, and if the packet from host A arrives at Tor2?
Okay, the question is, what if one of these two links fails? Let's say that this link to Tor3 fails, and for some reason the traffic gets routed to the Tor3. Okay. So in this case, we do still have a peer link over here, which is hidden behind my packet. But it will use peer link, and it will forward it to Tor2, and then forward it down to the host B. So because we are in part of the VPC domain, we are able to route traffic between VPC peers to forward it over the peer link so it can reach its own destination. Go ahead.
It's VPC peer, but we have
the question is, what if we have an orphan ports and orphan devices attached to? Would that come there? I'll come to that because there is plenty of more slides which I will explain, and that particular case is very interesting when you do when you have routers which are attached as orphan ports. So I'll come to that. Go ahead.
So we are talking about bridging and L2VNR, right?
Yes.
Why we are talking about packet here? It should be a frame.
I agree. No. The question is, why do I say, hey, we are routing the packet? Indeed, it's a frame. I agree with you. It's just my freedom to call them the same way. No, it's all good. So I mentioned bridging. So let's see how we do routing. In this case, we do have host C, which is in different VLAN. So this is VLAN 102. I didn't mention, but this is VLAN 101. So they need to do routing, inter-VLAN routing, which will happen here. So we need to use layer 3 VNI and layer 3 information. So in this case, we use the same advertisement. So that advertisement type 2 route does contain layer 3 information. So when host 3 sends the information, it will change destination MAC address to Anycast gateway address. So remember, in first couple of slides, we defined this MAC address. So because this packet is routed, it will reach here. Tor5 will route this particular packet and put it in the VXLAN header with source IP address of Tor5, destination IP of the VPC domain. And then we have VNI, which is layer 3 VNI, source MAC, destination MAC, which are router MAC of these through of Tor5 and one of the VPC peers. In this case, will be here the Tor3, which is this one on the left. So we route this packet. It will reach the destination, and any of two VPC peers will be able to deliver this information. So more interesting part, let's say what's happening when you attach router to a VPC peers or VPC domain. You advertise this networks, routers, using type 5 routes. So in type 5 routes, we have obviously the type of the routes, IP address of the network, of the subnet, and then we have layer 3 information, layer 3 VNI, a layer 3 route target, and we do advertise it with the same VIP address in this case. So we are still representing both of the VPC peers with this advertisement. So what has happened? There is certain deficiency which are happening in this case, which I'm going to explain in next couple of slides. So what you need to do is to assure that both of the VPC peers are synced to the same, they are having route to this network. So where is the issue here? Let's say that our host C sending traffic to our subnet X. This is a router attached with 192.168.10/24. So we have a whole subnet there. So when the router C sends the traffic, if it goes to router 3, which is advertised over here with this MAC address, router MAC address of this router, it will send it down to the subnet. So we are good. Our subnet has received this packet and we are good. However, what if it happens if it routes to Tor2, which doesn't have a connection between network or the router and that VPC peer? We will drop this traffic. We will black hole it. So that's that deficiency which I mentioned. So how you can overcome it? First thing is to dual home this network to both of the VPC peers using layer 3 point-to-point links. So both of the VPC peer learn about this network. But let's say that you have only single port which you can connect. So this is not a solution. What you can do is to create dedicated routing session between two VPC peers. So you pick an SVI and you say, hey, I will form the peering between VPC peers over this VLAN where these SVIs are member, and you form that routing connection and you put it in the appropriate VRF so this packet can be routed. So when the packet reaches Tor2 on the left side, it will be sent to Tor 3 and down to the subnet. So this is one way to overcome this. Go ahead.
Does that apply for fabric VPC?
Sorry.
That scenario, I have that same scenario, but I'm running fabric VPC.
I'll come to that. So the question was, if you run the same scenario with fabric peering VPC, I do have a couple of slides explaining this, so bear with me. So what is another point or another solution here? It's to use that primary IP address to advertise this network. So it's called primary IP or PIP. So what we do here in those same type 5 routes where we advertise these networks, instead of using WIP address, we are using primary IP address of this VTAP. So it's beneficial to type 5 routes where you're attaching the networks. And then you advertise this advertisement. Your type 5 routes are advertised with PIP address and router MAC. So how do you configure this? You advertise, in the BGP information or BGP configuration, you will say advertise PIP as a command, as a CLI. And then inside of your interface NVE1, you will say advertise virtual MAC address or virtual MAC. So your question is, what's this virtual MAC? So before I go there, just to repeat what I said before. So with this advertise PIP, any of the type 5 routes, which are our subnets networks, are advertised with PIP. Anything which is attached as a host, which is type 2 route, it's still advertised with the VIP address. Our VMAC is basically derived from the IP address of derived from VIP address of the VPC domain. So first 2 bytes are 0200, and then the last 4 bytes are derived from the VIP address in the hexadecimal or hex format. So for our, I'll show you an example where we translated this VIP address, which is 10.200.200.123, into a MAC address of this format. So bear with me. So to come back to the routing, we have advertised this subnet X with type 5 route, but we have used next hop of this Tor 3 over here to advertise it as a PIP address, primary IP address. And then we use the router MAC of this router of the Tor 3 to advertise this route. So any traffic advertised by Tor 3, which belongs to subnet X, will be always attracted to Tor 3 and forwarded down to that network subnet X. If we dual home this subnet, we can do that as well. Both of the VPC peers will advertise this subnet, but they will use each identical router IP, so primary IP address, and then unique RMAC address to advertise these routes. So no matter which path you pick, you will reach your destination, and you'll be able to load balance if you are like a spine or other Tor. So I'll come in a moment to VPC fabric peering, but I want to kind of touch base about BUM traffic, broadcast, unknown unicast, and multicast traffic being forwarded inside of the overlay when you have attached host to a VPC domain. So first way to do this, it's called ingress replication. With ingress replication, we take that BUM traffic, for example, let's say that's an ARP packet, and we replicate it on the ingress VTAP to all of the members of that same VNI. How do we know who are the members of the same VNI? We use type 3 routes, BGP VPN routes, to learn about all other VTAPs, and this is what's represented in this example. So we have type 3 route for our host 101, host A, which is advertised with layer 2 VNI and a VIP address. In the same VNI, we have host B, which is this one, 102, with layer 2 VNI. and then our host C, it's advertised, but it's in part of the different VNI, but it's still advertised, so we know we don't need to send it to that particular host. So, okay, before I go to multicast, so this is kind of the way. So if host A needs to send an ARP request and it's bridged, it will reach the VTAP. VTAP will know, hey, I have the VNI where host B is attached, so I will forward this, replicate it, and forward this to this particular host B or VNI, or VTAP where host B is attached. So that's one way of doing this. It might be not efficient if you have a large-scale fabric of hundreds of leaves or VTAPs, but smaller scale, it might be good enough. So another way to forward this bump traffic, it's multicast mode. So in multicast mode, we use PIM in underlay, protocol-independent multicast. And each of the VNIs, each of the VNIs, it's tied to a multicast address, which will be used in the underlay. So in our case, let's say that host A and that VNI 3001, it's tied to 239.0.0.1. I'll show you in the next example this. And then anybody who is part of the same VNI will be part of the same multicast group, so we can scale better. You can even map multiple VNIs into same multicast group. So what we need to know, we need to have single de-encapsulation nodes so we can avoid duplication. So one of the VPC peers or VTAPs inside of the VPC domain will be chosen to be a designated de-encapsulator. So it will learn SG and OIF. It will have multicast group with a source and outgoing interface, and the other one will not. It will have only SG but not OIF. So why this is important? When the packet reaches this particular peer, will be de-encapsulated and sent to the host. So let me show you a couple of examples over here. In this case, we do have host B sending ARP request to a host A, which is up there on the VLAN 101. So it will send ARP request to 192.168.101, which is IP address of the host A. And it will send it with its own MAC address, but it will send it with broadcast MAC address. So we use multicast mode in this case. Before we encapsulate this packet, we send it over the peer link to all of the orphan ports so they can learn about or respond to this ARP request if the request is for them. However, it is not. So we encapsulate this packet, and I said our destination is that multicast group which we tie to the VNI. So, and we run PIM inside of the underlay with Anycast RP on our spine. Once it reaches the spine, spine replicates this packet and sends it to the rest of the VTAP. So Tor5 doesn't have VNI or doesn't have this 3001 or 30,001 VNI, so it will drop this packet. However, Tor1 does have that VNI and it does have that hosts, so we'll forward this packet to a host A. Host A will receive this packet. Oh, it is for me, so it will reply with unicast packet back to host B, acknowledging that ARP request. So this is one way of doing this when we have host B requesting somebody outside of the VPC domain. And the other way is for host A looking for the host B. So we switch around. We have the same, different ARP requests going to this particular host. Same format. When we encapsulate, we use the same multicast group to 39.0.0.1 with the same VNI, layer 2 VNI. Reaches the spine, spine replicates, it goes to Tor5. Tor5 doesn't have anybody in this VNI, so we'll drop this packet. And it will be attracted by Tor3 because that's the one which has routes from the spine, and it's our designated encapsulator. It will de-encapsulate the packet, send it over the peer link to the other orphan host, and it will send to the local orphan host, and then go down to the host B, which is the one which will reply to this ARP request with unicast information and forward it where it needs to go. Any question before I continue further? Okay. So there is something which is called VPC fabric peering. Can anybody tell me what it's missing in this diagram? Peer link. So a couple of you has responded. Thank you very much. It's correct answer. So as you can see, there is no peer link between these two VPC peers. So where the peer link has gone, we use rich connectivity between leaves and spines to transport that information, which are usually transported through a peer link using CFS protocol. As those are layer 3 links, redundant, we can use those and not waste additional links for the peer link. Your peer keep alive, it's still there. It can go as well over that layer 3 fabric, but also can be out of band management, so that concept doesn't change. So how does the VPC peers do know that this is fabric peering? We do configure VPC domain, and we do define virtual peer link. So this virtual peer link will have its own loopback, kind of third loopback, with its own IP address, which will be used to mark destination and source for the particular peer link or virtual peer link. And then we do define an interface port channel, which doesn't have any of the physical member ports. So no physical links will belong to this port channel. And we tell it, hey, you are a peer link over here. So the rest of the system knows, hey, the physical peer link doesn't exist, so I need to send it over the fabric. Any of the messages I need to send over the fabric. But how do you ensure that? On the uplinks between leaves and spines, or on the leaves on the VTAP, uplinks you configure with port type fabric. So we know that those CFS messages encapsulated and needed to go over the peer link will go over this fabric links to reach to the other destination. So it's a configuration concept which needs to be applied to both of the VPC peers. So how they are advertised to the rest of the fabric, we still use the same VIP address. So if those are 1, 2, and 3, we will use IP address which is 10.200, 200.123. So same concept applies here. However, when we talk about advertisements, we do change the concept of advertisements. So any type 2 routes attached over the VPC will be advertised with VIP and VMAC. So similar concept as before. However, if you are type 2 host or your host attached over the orphan port, you will be advertised with the PIP and router MAC. Why? Because you want to attract only traffic to yourself if you are the one who needs to receive that traffic and not attracted to both of the VPC peers. If you are type 5 route, either that you are attached through a VPC or to orphan port, you will still be advertised with the PIP, primary IP address, and router MAC. So to kind of reiterate this, type 2 routes for all of the hosts are advertised, if they're VPC, they're advertised with VIP, if they're orphan ports with the PIP, and then type 5 routes, again, they're advertised with the PIP, no matter if they're VPC attached on orphan ports. So how the bridging works for the VPC fabric peering. In this case, we do have host A talking to host B. Because our host is attached to VPC peer, we do advertise it with VIP address, and we advertise it with the VMAC address. Remember, I mentioned that we use 0200, and then we convert this IP address, VIP address into hexadecimal format, and we fill up the rest of the bit of this MAC address. So that's how this host B is advertised. We use the same IP of the VTAP on Tor 1, destination IP, it's VPC domain, layer 2 VNI, and the same host MAC address similarly as before. So concept doesn't change. However, what is going on when we are sending information about orphan ports? So in this case, I did make a typo over here in this slide, so I'll try to explain in words. So Tor 1 will send it to the spine, and then Tor 2 will be the one attracting this traffic. So I did put 103, it should be 102. Sorry about that. And then 102 would be a MAC address of this particular peer. So this is how this particular route is attracted to this particular Tor, where this orphan port, orphan device B1, it's attached. If it's the second one, B2, same concept applies. We advertise only that one. So this one is correct, 104 and 04 for Tor 4, and we attract only to that particular Tor, this particular bridge traffic. If we do have a router traffic, I'm having two subnets, subnet X and subnet Y. So subnet Y, it's advertised with type 5 route with its own network address, layer 3 VNI, and then 104, which is IP address of the Tor 4, with router MAC of this Tor 4. So somebody in subnet X will send information to Tor 3. Tor 3 will encapsulate this packet with layer 3 VNI destinated to Tor 4, 104, because it's advertised here. And then when the spine sees it, it knows that it needs to forward it to Tor 4, and it will reach subnet Y in this case. So there was a question earlier, does this make sense? Yeah. So that's how routing is done with VPC fabric peering. Again, I do have a lot of hidden slides, and they're explaining some of advanced features which are present in the VPC peer. In the VPC with VXLAN. So please look at those and absorb. And you have WebEx, so ask me any questions if you may have. I'll be here after the session. But some of the key takeaways which I wanted you to take out of this session is that using VPC, you dual home your hosts, and you send full bandwidth with both of the links to both of the VPC peer. So you are using all the money which you invested in those switches. You do dual home everything, not just host. You can dual home firewalls and other appliances inside of their fabric. And fabric peering does allow you more flexibility because you don't need to create that physical peer link between two of the devices. With this, I would like to recommend you a couple of sessions in this Cisco Live. So later today, there is a session about RFC 5544, which is IPv6 unnumbered. So that underlay doesn't have to be IPv4, it can be IPv6 as well. And if you build it with IPv6, you can use RFC 5544 to reduce amount of IPv6 addresses which you use. As well, Lucas, it's on Friday at 8 a.m. It's talking even more detailed understanding of type 2 routes, type 5 routes, and as well packet walk there. So go ahead and look at that session. It will be useful to understand VXLAN in even more details. Fill up your survey, especially tell me what you like in this session, what you didn't like, so I can improve for the next time and provide you better understanding. If you want to take a look at the Learning and Certification Lounge in the World of Solution for anybody with certificates or want to be certified in the future. And then I'll be here for the rest of the Cisco Live if you want to schedule MTE with me, meet the engineer. We'll be in the World of Solutions for the demo over there, just for me or anything else which you might want to find out there. And if you have missed any of the session in this Cisco Live, just go and look at on-demand library. There is a link on the bottom over there. Search this session or any other session, and I'm pretty much sure they will be useful. So thank you very much, and enjoy the rest of the Cisco Live.